epsilon sub zeta naught plus 2, blah, 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 blah. And this is going to keep on going, but this function is going to get stuck again. And this time, the function is going to get stuck at zeta 1. Now, this might not be so clear why it gets stuck at zeta 1 this time, but it's basically for the exact same reason. If we think of this function kind of as an epsilon building function, we can create finite nestings of epsilons, but we can never create an infinite nesting of epsilons. So if you can imagine us creating like bigger and bigger epsilons, we have epsilon, 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 zeta naught plus 1. Because remember, now we have zeta naught in our toolbox because of this, this ordinal right here. This ordinal got us zeta naught. So now we can start using that in our function, basically. So we can keep on building bigger and bigger epsilon numbers, but we can never get to this infinite nesting of epsilons with the zeta naught plus 1 at the very bottom. Or another way of writing it would be zeta naught to the zeta naught to the zeta naught, blah, 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 blah. Either way, we can never get to, or actually, no, sorry, okay. Disregard what I just said. This is not the same as this, whatever. That would just be this here. That would just be the epsilon zeta naught plus 1. So forget what I said about the infinite tower of zeta naught. Okay. We can't build an infinite nesting of epsilons with zeta naught plus 1 at the bottom because we can't get an infinite nestings of epsilons. So the function gets stuck. This time, instead of zeta naught, it gets stuck at zeta 1. So this is just going to equal zeta 1. So now, capital omega bails us out again. It gets the function unstuck. What we can do now, let's leave that bottom function there, is we can do psi, capital omega, and then add another omega in here, because we're allowed to do that, because we can do anything in S with addition, multiplication, exponentiation. We can do that. So now this is going to truncate to just capital omega times 2, okay? And this is still just going to equal zeta 1. But now we can do stuff like this, right? Because that's allowed. That's part of, as we did multiplication and addition, that's allowed using S or whatever. Now this is going to equal the first epsilon number after zeta 1. We can keep on going, replace A in here and A here. And this time the function is going to get stuck at zeta 2. Because now we have zeta 1 in our toolbox, we can imagine we can get anything up to an infinite nestings of epsilons with zeta 1 plus 1 at the bottom, but we can't get an infinite, because the infinite one would be zeta 2. So the function is going to get stuck at zeta 2. So you can imagine kind of like a repeated unsticking of the function by adding in another capital omega each time. So if we were to write down, let's say omega times A. So this is like the number of times that we have to put omega in to unstick the function. This is going to equal the A minus 1th zeta number, basically. Which is what I have written up here, whatever. So I have some little guidelines up here, so I don't screw anything up. Okay. So what can we do from here? Well, we can keep on increasing this number here, getting bigger and bigger zetas. And we can go up, and we can even do infinite ordinal search. So we can put an omega here and get the zeta to omega function. And this function gets stuck again, but this time it gets stuck at the limit of the zetas. So if you think of this now as kind of like a zeta building function, it builds bigger and bigger zetas. So you're allowed to get stuff like nested zetas, whatever, but only finite nested zetas, right? So the infinite nested zetas, I don't know if I actually use this infinite ordinal. We call this one phi3 of 0, but another name for it would be eta naught. Eta naught is another term, and this is synonymous with phi sub 3 of 0. So this would be eta naught. So this function gets stuck again at eta naught because we can't create an infinite number of zetas. So it's stuck at eta naught, which is just eta naught. Once again, we can unstick this function by using psi omega times omega, which truncates to psi omega squared, which is also going to equal eta naught. Okay. Okay, and once again, we can keep on going. We're allowed to do omega squared plus 1 or whatever. That's in our toolkit. So we can do that. And that's going to be our first epsilon number after eta naught. And we can do any of the stuff that we did before, whatever. So we can create zeta naughts from this, whatever. We can do like a bunch of other stuff. We could put, with this function would get stuck at the first zeta naught function after the first zeta naught function bigger than eta naught or whatever. But for argument's sake, whatever, I'm just going to show you what happens because there's a whole like bunch of ordinals you could do. If I went through every single one of them, it would take forever. So we'll just do the big ones. We'll just do the interesting ones, whatever. So what happens when you increase this number here, whatever? So let's say we go all the way up and we end up getting like an omega squared times an omega, which is equal to omega to the 3. Well, this is going to equal, this function is going to get stuck at the limit of the etas. So basically, think of an infinite nesting of etas, which is going to be, I don't have a Greek letter for that, so I'm just going to call that what it is, which is phi 4 of 0. So you can see a trend here where, in general, psi omega to the a is going to equal phi a plus 1 of 0. So now this, you can kind of see this as kind of like a phi building function, and we can go up through all of the phi's, even infinite phis. We can do nestings of phi functions, and of course the limit of that, the limit of the nestings of phi's, is going to equal gamma naught. So this function is going to get stuck again at gamma naught because we can create all phi's nested phi's, but we can't create an infinite number. So, and the infinite number, of course, is our gamma naught. So let's get stuck at gamma naught. And once again, this is also going to equal gamma to the gamma. We use this to bail us out so that we can continue on. This all equals gamma naught. So as usual, we can do psi gamma to the gamma plus 1. So I'll write that down. Psi gamma to the gamma plus 1. It's going to be our first epsilon number after gamma naught. We can keep on going up like this, whatever. We can go through all these numbers here. So we have gamma naught plus, this plus a would be gamma naught plus a. Go through the zetas, go through the a's, go through all the phi functions. Some other noteworthy points, whatever. So when we get to stuff like this, so gamma to the a, this would be the first phi functions after, yeah, so this would get stuck at phi gamma to the a plus 1, I believe. I think so. Pretty sure I wrote that down. Anyways. There's intermediates, whatever. There's lots of intermediates ones that you could write down or whatever. Like even some of these are a little bit hazy with me or whatever. But we'll write down the noteworthy ones. So this one I know for sure. So psi of gamma to the gamma all times a. That's a way of writing down the fixed points of the gammas, whatever. So gamma of a, whatever. So you could think of this as kind of like a gamma building function type of thing. Which is also, as we know, we can write down an extended Veblen notation. A Veblen notation of 3 arguments with an a right here. That's just another way of writing that. And this is where we start to get past things that we've done before. So to get to the Ackermann ordinal, or the ordinal that's the limit of the gammas, we can do psi gamma to the gamma squared. Okay, so now on to infinite collapsing ordinals. So this is basically a way where we can get far, far, far beyond anything we've done so far, and we can do it within a single function. So don't worry about this too much. This is kind of just for me, just to remember where I am and everything. So first thing we're going to start with is we're learning an entirely different thing here. So we're going to start at the very beginning. I want you to imagine a set S, and this is going to contain 0, 1, omega, and this time something new, capital omega. Now I want you to imagine this is kind of like our toolbox. This is what we're going to use to construct the ordinals. And basically what we're allowed to do with our toolbox is we can take anything from inside this and we can use addition, multiplication, and an exponentiation basically. So we're going to define our first set, C0, so C of 0. And this is going to be exactly what I just said. This is going to be anything that we can do in here with addition, multiplication, and exponentiation. So we're going to have this is equal to things like 0, you can do 1, you can do 2, omega plus 1, omega times 2, we can have omega to the omega, omega to the omega to the omega, blah, 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 etc., etc. And we can even have things to do with this one here. So we can have this plus 1, capital omega plus 1, capital omega to the capital omega. But we're not going to worry too much about this here because this ordinal is going to come in later. For now, we're just going to kind of deal with these ones here. So there's a whole bunch of things that we can do with, and these are just a few of them. So these are a few things that C of 0 contains. Now, what's the first ordinal that cannot be reached in this way? Well, it's going to be an infinite tower of omegas, right? Because we're only allowed to do a finite addition, multiplication, exponentiation, whatever. So an infinite tower of omegas will be the first infinite ordinal that is not accessible in this set. So we're going to give that a name. We're going to call that psi of 0. Remember, this is psi, not phi, like we had in the previous ones, Veblen notation. So this is different. This is psi. And this is our collapsing function, basically. So we're going to call psi of 0, our first function, is going to be the first infinite ordinal unreachable from C0, which is going to be an infinite tower of omegas, which, as we know, is epsilon naught. Okay, so now moving on, we're going to go to C of 1. Now, C of 1 is our previous set, so C of 0, and I'm going to use the union symbol there. So this just means this in addition to that. So this combined with any operations of this using addition, multiplication, and exponentiation, basically. So we can have anything that we had in here, plus we can have things like, epsilon naught, we can have epsilon naught plus 1, epsilon naught times omega, epsilon naught to the epsilon naught, epsilon naught to the epsilon naught to the epsilon naught. And we're going to label the first infinite ordinal not accessible from this one as psi of 1. And this is going to be an infinite tower of epsilon naughts, which is equal to epsilon 1. Now, before I go any further, because this is something that tripped me up, how does this equal epsilon 1? Because I taught you that an infinite tower of omegas with epsilon naught plus 1 is equal to epsilon 1. Well, the answer is they're both equal to epsilon 1. And before I go any further, I'm going to show you why. So it's important to write some of this down, or if you want to kind of reference this, so I'll ask you to write this down. Wonderful thing about video is I don't have to wait for you guys to write it down because you could just press pause. Good stuff. Okay. So a small aside, showing that things like an infinite tower of omegas, blah, 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 with epsilon naught plus 1 at the top, is the same as an infinite tower of epsilon naughts. So why is this? Okay, well, let's take a small example. Let's take, if I were to have epsilon 1 diagonalized to 3, if I were to have something like omega to the omega to the omega to epsilon naught plus 1. Well, let's evaluate this. Epsilon naught plus 1, we can use rules of exponentiation or whatever. We can take omega to the epsilon naught times omega. And then, okay, so let's do that. I'll try not to do too many steps in my head here. I'll try to write this out. Times omega. Well, now we have an omega to epsilon naught all by itself, which, as we know, because epsilon naught satisfies the equation omega to the a equals a, this just collapses into omega naught. So let's just get rid of that. This just turns into epsilon naught. So now we have an omega to the epsilon naught times omega. We can use another rule of exponentiation with this part here, and we can turn this into omega to the epsilon naught to the power of omega. So that's another property of exponents or whatever. If you have this times omega, this is the same as putting this in brackets, this to the epsilon naught, all to the power of omega. That's another thing we can do. And once again, we have an omega to the epsilon naught all by itself. This collapses into just epsilon naught, so we get omega to the epsilon naught to the omega. So what do we do now? Well, we're going to use a property of infinite ordinals that's a little bit useful. If you remember, 1 plus omega is still equal to omega, right? So I can sneak a 1 in the beginning of here, so I get omega to the epsilon naught. 1 plus omega. I'm allowed to do that because this is still equal to omega. And I can do that little trick because it'll help me with this rearrangement type of thing, whatever. So now we're going to use rule of exponents again. So we're going to have omega to the epsilon naught to the power of 1 is just epsilon naught. And we're going to go times epsilon naught to the omega, because you see what I'm doing here, I'm using rules of exponents, so I take this one here to the power of here and multiply it here. Alright, so now I'm going to use this same rule that I used here, or whatever, so I have